Hello everyone, my name is Andrew Kim, and today I'm going to make a video about AP Physics C Unit 1 Kinematics. So this video would be the first video of the series of video for AP Physics 1. I know that our school does not provide the course AP Physics 1, but still we have the course ATCP, and majority of the students from that course will take AP Physics 1 this May. So I'm going to make this video in order to get you guys be prepared for the AP test. And I remember making very similar videos during the fall break, but those videos were more focused on school classes, whereas this video will be more focused on the AP exam itself. So if you're looking for some materials to study for the AP exam, then this might be very helpful. So let's get started. Okay, so our first unit, kinematics. Kinematics is basically a study of analyzing different variables, and the variables include velocity, displacement, speed, acceleration, and time. Now, we're going to see how each variables are related, how they're different, or how one variable can affect another variable. So before that, we have to know two essential terms, which are vector and scalar. So they're very similar, but they also have a big difference. Vector is basically magnitude plus direction, and scalar is just magnitude itself. Now, it might be confusing if I simply say something is magnitude plus direction and the other one's just magnitude, but it's easier to think it this way. Vector and scalar are two categories to separate variables. What variables? Well, there might be temperature, speed, velocity, displacement, height, those things. We have those datas or variables in science, and we want to differentiate those variables based on some metric. And that metric that we're using is whether it's vector or whether it's scalar. And what makes a certain variable vector and what makes a certain variable scalar? Well, that depends on whether the variable includes direction or simply has the magnitude. Now let's think of height. Is height a vector variable or a scalar variable? Well, height is a scalar variable because height does not have direction. Every single time, height should be above the ground or upwards. There can't be such thing like rightward height or leftward height, but height should always be upward. It always have the same direction, so it's pointless to notify the direction of the height. Thus, when we talk about height, we only say the height is 50 meters, the height is 30 meters. We only talk about the magnitude, thus it's a scalar. What about temperature? Well, temperature, it's the same. You only have the magnitude. There's nothing such as left temperature, right temperature, but there's only temperature. The temperature might be negative or positive, but regardless, still, you don't have direction in temperature. Then what variables can have direction? And now I'm going to introduce those things. First would be displacement. Now, when we say displacement in spoken English, there's no difference between displacement and total distance or total distance moved. Basically, if you say you moved a certain distance, then you assume that that means the same thing as displacement. However, what displacement means is it's simply looking at the result and the start. You don't care about what happens in the middle. It's like a test. You don't care about how much you studied, what processes you went. The only thing that matters is the grade. So in case of displacement, say you start from point A and you end at point B. There might be two routes. Route 1 is a very curvy route. Route 2 is a straight route from A to B, the shortest distance between the 2 points. In terms of displacement, the two routes does not have any difference because you're simply looking at where you started and where you ended. You started at point A and you started at point B. That's the displacement. Your displacement is rightward whatever distance this is. Let's say this distance is 10 centimeters. Then the displacement would be rightward 10 centimeters. Now you can realize how for displacement, I mentioned rightward 10 centimeters, not just 10 centimeters, but rightward. I included the direction. Thus, its magnitude, the distance, plus direction, rightward. So it would be a vector, not a scalar. Now, if you think about total difference, it's kind of different. Total difference is more like formatives because you actually care about the process. It's not only about the grade, the final grade, but it's also about what process you went through and how you can improve. Now, that sounds really sorry, that's nonsense. Anyways, so total distance moved is you actually care about which route you took. So route 1 again was a curvy route, and route 2 was a flat straight route. Now, if you think about the two routes, you can see how the first route is longer because it's curvier, whereas the second route, the straight route, would be shorter because it's simply the shortest distance between the 2 points. Thus, the total distance would be not 10 centimeters for both, but 10 centimeters for route 2 because that's literally the route you took. But for route 1, it will be much longer, probably like 100 centimeters or even longer than that. So again, total distance moved is literally how much distance you actually moved. And displacement is simply how much, like where you started and where you ended. Because I mean, if you think about the word itself, it is this placement. This is like the difference, and placement is your location. So it's simply looking at the difference in your position, where you started, where you ended. So that's why when you talk about displacement, it's a vector because you have to tell which direction you moved and how much you moved. Whereas in terms of total distance, it's impossible to tell the direction. Why? Some people might think it is possible to tell the direction because in this case, in this drawing, you might be able to say the total distance. You might be able to say the direction of the total distance moved is rightward because you started from A and you ended up at B, which is more right compared to A. However, what if you took a route C, which moved the third route, which moves like this? Now, can you say that total distance moved is rightward? Well, if you only look at the starting point and the end point, which is displacement, yes, you did move right. However, if you think about literally what path the person took to move from A to B, you can realize how initially the person starts moving leftward. So it's impossible to say that the total distance moved is rightward because yes, you started from the left and ended up at right, but that's displacement. Now you're looking at total distance. You want to look at every single move the person took in his journey. And that move includes rightward movement as well. So it's impossible to say that it's impossible to notify the direction for total distance moved. That is why displacement is a vector, whereas total distance moved is a scalar. So when the question asks what the displacement of this object or person or whatever, then you just want to look at the initial point where you started and the final point where you ended. Whereas if the question asks you what the total distance moved is, then you literally want to calculate the length of the route, like how long the route actually is. Now let's move on. Now we have to talk about something a bit more complicated, which is velocity. Now, again, in spoken English, velocity and speed literally means the same thing. They both mean how fast a certain object is. But in physics, they have a slight of a difference. Velocity means change in the position, or well, it's not really change in the position. I have to rephrase this. It's more like ability to change its position. If you think, so let's think about it this way. Let's think about a ball with a high velocity. What does it mean if a ball has a high velocity? It means that the ball is moving very fast. In other words, the ball's position is changing very fast. The ball has a great ability to change its position. Now, the speed, in the case of speed, it's not its ability to change the position, but it's more like the ability to move on the route. Now, when I just explain it with words, the two velocity and speed both sound very similar. However, if I express this in equation, you might be able to see the difference more clearly. So velocity, v, you literally calculate it by the change in displacement over time, whereas for speed, you calculate it by total distance moved over time. So that's the difference. When you're talking about speed, you're literally looking at how fast the person or object is moving on its path or on its route. Whereas velocity is more like displacement over time. So it's asking the efficiency. How efficiently is this object or person moving? So let's think about this example. There's a train A, and this train continues rotating on this circuit, on this path. Now, this train might be very fast. If this train is very fast, it means that the speed of this train is extremely high. Why? Because the total distance moved over a given time of this train would be really high. However, the velocity of this train would be terrible because displacement is where you started and where you ended. Now, if you calculate the displacement, it will be zero. You start at this point and you end up at this point after rotating one route. So in terms of velocity, this train is very slow, whereas in terms of speed, this train is very fast. So speed is more like asking its actual ability to move, its actual how fast or slow this object is, whereas velocity is more like asking how efficiently is this object moving. Now, this is actually a very tricky term. And in fact, unless the question specifically asks what's the difference of the speed and velocity, or unless the question like specifically, unless it's very obvious that the question wants to check if you know the difference between the speed and velocity, most of the cases, even in physics questions, they just use the two terms alternatively. Like even if so velocity, sometimes the question might simply say velocity when it actually means speed, and it might say speed when it actually means velocity. So this is not a very important thing to know. Even in fact, a lot of YouTube videos or a lot of study guides never talk about this, but still there might be some weird MCQs that actually ask the difference between the two terms or stuff like that. So just keep this in mind for those tricky MCQs. So again, velocity or speed is basically how well the object can change its position, but velocity is more focused on the displacement, where speed is more focused on the total distance moved. Now let's move on to the acceleration. Now acceleration is, again, ability to change its velocity. Now let's say a car has a high acceleration. What does it mean? Does it mean that the car is fast? No, it does not mean that the car is fast. It means that the car's ability to get faster is great. The car is gradually getting faster and faster and faster. Thus, the car might, even after getting faster, the car might still be slow. But what you really want to see in acceleration is whether the car is getting faster than before. So now velocity was more like change in displacement, whereas acceleration is change in velocity. I hope you guys get this. So if you, in terms of equation, it would look like this. Acceleration, A equals to delta V, difference or change in velocity over time. So how well this object can change its velocity. Now, in terms, now, after looking at each variable, now we have to see the relationship between different variables. So first of all, let's look at the relationship between position and time. Now, some people might be confused because I've never talked about position, but in fact, position is literally a component of displacement, because when you discuss about displacement, it's the difference in the starting and the ending position, right? So basically, position means something very similar to displacement. So now let's look at this graph. What does this graph tell us? Well, as you can see, as time goes on, the position of this object increases proportionately. This tells us that, first of all, let's think about velocity of this object. Would the velocity of this object be positive, be zero, or negative? Well, as you can see, the object is moving in a positive direction, which tells us that the velocity should be positive. If the velocity was negative, it would be moving in the opposite direction. So it would be moving like this. The graph would go downward, not upwards. Now then, would the velocity be increasing, constant, or decreasing? Well, in order to think about that, we have to see how the position is changing. Is the position change? We know that the position is increasing, but is the position increasing more later than before, or is the position increasing on the same rate, or is the position increasing less than before? Well, if you look at the graph, you can see how the position increases on a constant rate. At when t is equals to 1 second, 1 second after the object started moving, and when t is equals to 3 seconds, so 3 seconds after the object started moving, you can see how the object is still increasing its position on the same rate because the slope is the same. This tells us the velocity is positive. That's why the object is moving towards positive direction, but the velocity is stable. The velocity is not increasing, because if velocity was increasing, that would mean that later, when t is equals to 3, the position of the object should change more, because again, velocity is the ability of the object to change its position. So if velocity increases, then velocity at 3 seconds should be greater, meaning that the object's ability to change its position at 3 seconds should be greater. Thus, the slope at t equals to 3 should be steeper. However, it's not. The slope is the same when t is equal to 1 and t is equal to 3, which tells us that the velocity is constant. Now, let's look at the graph below. This time, it's not a position time graph, but it's a velocity time graph. Now, what's interesting is, unlike the graph above, over here, velocity is increasing. Yes, in the graph above, the position was increasing, but velocity was constant, and I just explained that like 60 seconds ago. But on this graph, you can see how the velocity is increasing. Now, what would happen if velocity is increasing? First, let's think about position. Would the position be increasing or would the position be decreasing? Well, the answer is so obvious. The velocity is positive, meaning that the ability of the object's ability to change its position is positive. Thus, the object is changing its position towards positive direction. So obviously, the object would be moving towards a positive direction. Thus, its position would be increasing. However, what about the rate of the increment? In other words, would the object's position increase more later or more initially? Or would the rate of increasing the position of the object would be the same? I hope this is not confusing. Well, to tell you the answer, the object will change its position better later compared to the beginning. Why? You can see in this graph how velocity is greater later than the beginning. Later and beginning might be kind of confusing, so I'll assign a certain number. Let's use the same number again. 3 seconds, 1 second. You can see how velocity at 3 seconds is greater than the velocity at 1 second, meaning that the object's ability to change its position at t is equal to 3 seconds is greater than the object's ability to change its position at 1 second. Thus, the object's position, if you draw a PT graph, position time graph, the slope of the position would be greater when t is equals to 3 than when t is equal to 1. As you can see, when if you look at this graph over here, when t is equal to 1, the slope is only like this. It's relatively flat, whereas when t is equal to 3, the slope is much steeper. Because again, slope shows how much the position is increasing, and how much the position increase is velocity. Now, so what we just did is using the VT graph, or analyzing velocity, we were able to make a conjecture and how the position would change. Now, let's do something opposite. Using the velocity time graph, let's analyze and make a conjecture on how the acceleration would change. Well, what is acceleration? So velocity was the object's ability to change its position, whereas acceleration was the object's ability to change its velocity. Now, if you think about that, if you think about here, if you look at this graph, when t is equal to 3 and when t is equal to 1, yes, velocity is increasing, velocity is changing, but they're changing at the same ability. They're changing at the same rate. Why? Because their slope is the same. Yes, they're increasing, but how much they increase is constant. Thus, their ability to change its velocity when t is equal to 3 and when t is equal to 1 is the same, meaning that the acceleration when t is equal to 3 and when t is equal to 1 should be the same. Thus, acceleration should be constant. Now, would the acceleration be positive or negative? So we realized that the acceleration should be constant, but we never figured out whether the acceleration will be positive or negative. Well, to tell you the answer, the acceleration should be positive. Why? You can see the velocity is increasing, and again, the definition of acceleration is the object's ability to change its velocity, and the velocity is changing positively. Thus, the acceleration should be positive. And again, the velocity is changing, but it's changing at the same rate. In other words, same ability. Thus, the acceleration should be constant. So again, acceleration should be constant and positive. So actually, the graph below is literally the same graph as the graph above, except it shows the acceleration of the object, not the velocity. So what's really important when you see the graph is you should try to understand what's actually happening. You should try to picture how the object's actually moving and try to make conjectures in how velocity, acceleration, and position of this object would change over time. Now, if this thinking process is too confusing for you, then there's an easy hack. But hack it's merely a hack. It can't be the ultimate solution every time, because hack, you can only memorize a certain amount of hacks, right? You can't solve every problem with hacks. So I recommend relatively easier units like unit 1 to be dealt with mind processing, not hacks or just formulas. But try to use hacks when it gets to later units, when it gets harder, like torques. But still, for some people who might find kinematics harder than the other units, I will introduce the hack. So how the hack works is, let's think it this way. What is the most inferior of the three? So we have position, velocity, and acceleration. Which one is the most inferior? Well, inferior, superior might not be the right word to use in this situation, but I'll just name it this way so that you guys can memorize better. Well, I'll say it's position. Position is the most inferior because basically it's the most basic variable of the three. Everything starts from position. With position, you can calculate velocity, and with velocity, you can calculate acceleration. So I would say P is the most inferior, that followed by V, and A would be the most superior because acceleration is above the other two variables. You need the other two variables to calculate acceleration. Now, when you have this chart or when you have this list, then what you can find this relationship that the slope of the inferior one is the value of the superior one. So the slope of PT graph is velocity. And the slope of velocity time graph is acceleration. So if you look at these two graphs again, you can see how the slope of xt graph was constant. That's why velocity was constant. If you look at vt graph over here, again, the slope was constant and positive. That's why acceleration was constant and positive. So this is one easy way to memorize, but it's not too hard to mind process it. So I'm recommending you guys to not just memorize it blindly, but try to understand how object moves and use that understanding to find a relationship between P, V, and A. But if you find the mind processing harder than just memorizing, then this is the shortcut. Again, if you have P, V, and A, then the slope of the inferior variable would be the value of the superior variable. So the slope of position would be the velocity, and the slope of velocity would be the acceleration. You can also go the other way. If you draw an AT graph, then the area under the graph is V. And if you draw a VT graph, then again, the area under the graph is position. Now, you might think how this works. Well, it's literally the opposite way. If you've taken calculus, then you will understand, because it's the opposite way of using slope, which is integrals, which is finding the area under the graph. But if this is too complicated, then just forget what I just said. So yeah, that mind processing is really important. Now, finally, we have the three formulas. Now, again, I really hate memorizing formulas because these are actually all really intuitive. They're like, they make sense. You don't really have to memorize these to use it. But just in case, because if it's an exam, you have the clock running, then you might feel more pressure and it might be hard to process things on your mind. So it's always good to memorize formulas or be familiar with the formulas, because I'm pretty sure these formulas would all be on the formula sheet. So you won't necessarily have to memorize it, but still you should be familiar what variable means what and when you can use this formula. So let's look at the first formula first. Vf equals to Vi plus A delta T. Now, Vf is velocity final. In other words, the final velocity. Vi is velocity initial, or the initial velocity. A is acceleration. Delta T is time, but the change in time. Now, delta is a Greek alphabet, and what it means is it basically means the change. So when it's delta T, it means the change in the time. So the formula Vf equals to Vi plus A delta T means the final velocity would be equal to the initial velocity plus the acceleration times the change in time. Now, why does this work? Well, if we think about it, it's very obvious. Again, what was the formula for acceleration? Or what was the definition of the acceleration? Definition of the acceleration was the object's ability to change its velocity. And its equation was A equals to delta V over T. Or delta T also works. Now, if you think about this, what would A times delta T be? Well, that would be delta V over delta T times delta T, because A is again equal to delta V over delta T. So you can substitute this into A. And if you calculate this, you can cancel out delta T, which leaves you delta V. Thus, you can know that A times delta T is equal to delta V. A times delta T is equal to delta V. So what you can change this equation into Vf equals to Vi plus delta V. Now again, what does delta means? It means the change in velocity. Final velocity is equal to initial velocity plus the change in velocity. Very obvious, right? Final should be equal to initial plus the change. That's so obvious. Even in English, it makes sense. Of course, this formula works. This is how you prove the formula. This is how you understand the formula. I think this process is very important. Oftentimes, teachers just tell you the formula or just give you the formula sheet, but it is important to know and understand what this formula actually means. This formula basically means that the final velocity is equal to the initial velocity plus the change in velocity, which is A times delta T, because A is not equal to, but the definition of A is the ability of the object to change its velocity. So the ability times time would be the change in velocity. Now let's look at the second formula. Delta D equals to VI delta T plus 1/2 AT squared. Now, in order to prove or explain this formula, you need to know a little bit about integrals, or you need to understand this part, how the superior graphs, the area under the superior graph is equal to the inferior variable, which might be kind of confusing. Plus, this video already exceeded 30 minutes, so I don't want to get too deep. But let's just think it this way. First of all, we learned in elementary school, probably middle school, that delta D, or the distance moved, is velocity times time, which is literally this part. Delta D, or displacement, equals to velocity VI times delta T. However, this formula that you learned in middle school assumes that the velocity is constant. It does not take consideration of the acceleration. Thus, this first part of the equation only accounts to a situation where acceleration is zero, when the object is moving on a constant velocity. However, now we're dealing kinematics. We are actually taking account of acceleration as well. Thus, we would have to add the distance moved by the acceleration, and that is 1/2 AT squared. If you ask me why, then I would again have to explain that it's because of this integration part, and it's kind of hard to understand, so I'll just skip that part. So again, basically what this formula means is that the distance moved is velocity times time plus the additional distance that you moved because of the acceleration. If you didn't have the acceleration, then again, the distance moved would obviously be just the velocity times the time. Now let's look at our last formula. Now, I hate the last formula because it means nothing. It has no physical significance, but it's simply a mathematical formula made by the two formulas above. Now, what this means is, if you look at this formula, you would be able to notice how you have delta D over here. Now, right in the formula above, we know that delta D is equal to VI times delta T plus 1/2 AT squared. So in this delta D, we can substitute this instead, which means VF squared or VI squared plus 2A delta D would be equal to VI squared plus 2A times not delta D, but the substituted value, which would be VI delta T plus 1/2 AT squared. Now, what's interesting is if you unravel this complicated polynomial, then what you get is VI squared plus 2A times VI, 2A VI, delta T plus 2A times 1/2 AT squared, which is A squared T squared. Now, this is very, very interesting because, in fact, you can factorize this equation. VI squared plus 2AVI delta T plus A squared T squared is, if you factorize using perfect square, you get VI plus AT to the power of 2. Because I'm pretty sure you know this formula, A plus B squared equals to A squared plus 2AB plus B squared. This literally works right over here. AT squared, VI squared, and 2AT times VI. So you can factorize it like this. Now what's interesting is if you look at the thing inside the square, VI plus AT, what is VI plus AT equal to? VI plus AT equals to VF. Thus, instead of VI plus AT, you can substitute VF inside here, which would give you VF squared. VF squared, VF squared. They are the same. This is how you prove it. You can see how there's zero physics involved in explaining this equation. You simply use mathematics, use factorization of polynomials and the two formulas above in order to induce this formula mathematically. It has zero physics concept involved in it. That's why I hate this formula. That's why I never actually use this formula in questions. But obviously, there might be a situation where if you memorize this formula, it can be very handy. It might reduce multiple steps in your calculations. So of course, it's good to memorize. But anyways, so that's it for the first unit. The video actually got really long. I was expecting it to be about 15 to 20 minutes long. Apparently, I doubled the time, but it's, I believe, because there's a lot of content involved. I'll make the second video as well. So watch that video too. Thank you for listening to my review session, and don't forget to have a great day.